For those who are subscribed to me because of my math content, I finally have another video. I usually don't like to upload math videos unless it's something new that I invented. So that's why it's very rare that I do upload one. But this is basically going to be a new method, and it may not be new. Maybe some people thought about it in the past or like, this is just totally worthless. It could be that, but it is a way to interpolate any data set into a continuous function. And this data doesn't have to be just single variable. It can be multivariate. It doesn't have to be the univariate case. And it's very, very easy to use. Very, very easy. I've never heard of something like this or seen this anywhere. So the multivariate case is not significantly harder than the univariate. It's almost identical. Alright, so that's enough of introduction. I guess I'll now get into it. I'm going to be using Mathematica just to show everything, but this is how it works. Alright, so what I have is a data set here where I assume that it's one variable, of course, for right now. I'm going to show a multivariate right after this so that those who want to like see if this is something that works or how easy it is, I just want to show it up front. And then the rest of the video, I'm going to be deriving it from scratch. And so therefore, it's like proving it, because the way I derive it is just so easy to see that it's going to stay the same for any number of data points that you plug in. And the scope of what it applies to as well. Basically, I have a data set here where I'm going to assume that x starts with 1 and goes to n. In this case, it's 7 different data points. And so I have a secret function here. I'm calling it secret because I'm going to show it soon, but we just want to maybe kind of guess what it is before we get into it. I want to see if you can guess it, or guess somewhat of its nature. I'm using n instead of x, but let's say it's like n equals 6, the sixth term, which is term number 6. It's 0.33. That's right there. So if I change this to like 2, it should be 5.33, right? Let me change it to 2. So you can see that it works. It works for all of them. I can just go ahead and do them all. 1, 7. We already saw 2, 3, 4, 5. We already saw 6, so 7. So there you go. Now let's go to a multivariate case, where this time we're going to have a special function px and py, because I'm assuming we have x and y as the independent variables that we call them. So basically, if you have like 5 different independent variables, you're going to need to have 5 different expressions like this all added together. We're going to find out what they are in the future. But for right now, we're just going to take a look to see that it works. There's 3 different data points here. So I'm going to plug in x equals 0, y is 230. I get 17. That's this value, which is this order triple here. So I'm going to do this one now. Negative 272. And I'm going to do this one is I. So the output can be imaginary numbers as well, or any real number for that matter. Okay, so that's how easy it is. So basically what the structure of the single variate, or univariate I should say, that's the proper term that I've read being used here, is that this is the x value, this is the y value it puts out for that x value. This is the x value, this is the y value it puts out. You subtract the previous y value that it supposedly is supposed to put out, which was 7. So that's how it works all the way down. And I have minus 0 here, but really you don't need to put anything for the first term in here. But notice that this is not the secret function evaluated some number of times the y value you're supposed to get plus the secret function times something else. It's almost that, but it's nested inside of a product of these. So it's kind of a much larger expression than what it appears to be up front. But when you write it like this, it's just that simple. So to add a new value to this, what I would do is just like press enter and then say plus and then have x at 8, and then I take this value, let's say a new value, I don't know, 533, and I'm going to subtract the previous y value, which was 0 there, and then I'm going to add another parentheses there, and that's it. So I press enter. I'm still at 7, but let me now go to 8. And so the same thing applies for here. I'll get to this later on, but basically the gist of this, the idea is that like this is 5.33 here, but this is negative 272. But I have it divided by 2. It looks identical otherwise, like they're very comparable otherwise. But all you have to do is divide by the number of independent variables you have. And you have to do this for every single expression like this. So this is 1, this is 1. So that's how the multivariate case works. Now, and of course square root of negative 1 is I. That's why I have square root of negative 1 here. But that's the idea. That's how simple it is. So to add a new data point, all I would have to do for here is just, and what I would have to do is, this is the x value that it's being evaluated at, and this is the next x value, and this is the next x value. These numbers here, these are just this number plus 1. So this is this number plus 1. And it's the same all the way down. But the one on the right is the x value, and then that's the y value, but you have to divide it by 2. That's all there is to it. So I add this here, and I'm going to say, well, this has to be 121 because that's this value plus 1, and let's just say we want like 150, for example, and we want to have, instead of I, we want to have 33. So I have to subtract this previous y value to put in there. That's how the formula works. So that is the x done. So now for the y, I can, let's say, do a similar thing where I add that, but now it's going to be p of y. And I have to say this number plus 1, and then I have to go to some number that's greater than that. So 234. And okay, so I have 33 that it's going to output. The previous value here is not square root of negative 1. It's going to be 17 over 2. And for each of these, I have to add a parentheses. And so now, when I press enter, I still get the previous output, but now the new value that I added in was, so when I press enter, I get 33. That's the value that we wanted to get out of this function. So why did I add, well, this was maybe explanatory, at least for later, that this number plus 1 is this number, but why did I put 150? Why didn't I put like 10 or something? The thing is, you have to put these in order. So once you figure out all the data points, you're going to have to list them in order according to the x value, so least first. So this, then this, then this, and then, so 150 is just some number that was greater than 120 and therefore greater than 121. You can have 121 itself if you wanted to. You know, if I change this to 121, that's greater than 120. So 121, then I just changed that to 121, and I still get 33 because now it's adjusted to that. So that's the only kind of like weird thing about it, but I mean, how hard can it be compared to other methods out there? Alright, so what I'm going to do now is I'm going to derive this first, and then I'm going to work my way into the multivariate case. What I told you right now is pretty much all there really is for the multivariate case. There's really nothing else to it. It's not any more complicated than what it already seems. So if you're thinking that I'm going to be building in complexity, it's quite the contrary. Okay, so this was the starting idea I came up with about 10 years ago. I was doing something for some Rubik's Cube formulas, and I noticed when I combine cosine of n pi over 2 squared, and I multiplied that by cosine of n pi over 4 squared, then I could somehow write expressions to come up with sequences for something, to find like the nth term of something. It kind of helped me out in that way. But then recently I said, let me try to make it into some type of interpolation or curve fitting. And so that's what I'm doing right now. Okay, so basically cosine of n pi over 2, the only thing you have to notice is that when you output, this is values evaluated at integers 1 through 32. So this is it evaluated at 1, and this is evaluated at 32. So the thing to notice is that 1 starts at 2, and it keeps going at every single even number from that point. So cosine of n pi over 4 squared. This, it's going to be 1 at every 4 numbers starting with 4. So 4, 8, 12. And the thing to notice about this also, but there's a relationship between these two, because basically what I'm going to do is I'm going to multiply these two together. So when you multiply these two together, this 0 right here is going to make this 0. This 0 here is going to make this 0. And this 0 right here is going to make this 0. So then this 1 right here multiplies with this 1, and it's going to stay 1. So we'll get to that in a little bit, but that's just something to keep in mind right now to notice between these two, is that we want to have, like, this number right here is greater than this number. We want the greatest number to have a 1 in some slot. This is going to be, so this, whatever number is here, the 1 is going to be in that slot in every multiple of that from that point. The same for this one. But when we're looking at, like, if we're pretending 4, we're going to go 2, 4, 8, 16, 32, 64, 128, powers of 2. What we want is to have 1 to be at this slot number. This is 4, 1 needs to be there. And also for all previous ones, not like ones, I mean all previous expressions. So if this was divided by 16, we would have divided by 8, and then we would go up more, divided by 4, and then divided by 2. We want all those to have 1 at this slot number 4 as well, if that makes any sense so far. And then we want to have every single one of them previously, before that, have 0 to cancel out all of these that are not this 1 when we multiply them together. So this is basically what I'm saying. When we multiply cosine of n pi over 4 squared times cosine of n pi over 2 squared, we're just going to have 1 at every, starting at 4 and every multiple of 4 from that point. So the idea is this. This is an expression we have. The previous expression we have will actually be this. So this is complete. This is complete. So what's going to happen is we're going to add these together. So let's say that we, just to kind of distinguish it and not make it ones anymore, let's say that we have 3 for the first value that we want to fit to our curve. And then the second value that we want to fit to our curve is, I don't know, 5. What we want to do is just simply add these two expressions together. We're not multiplying anymore. These are the two things that we multiply together to make the zeros cancel everything except for the 1 before. But now that 1 has become 5. So now all that remains is 5. But these are two separate independent variables, or let's say x values, that we want to fit to our output. What you see here is the output of the function that we are using to interpolate. So we're going to add these two together. The number at slot number 2 is going to be the first number in the data set. And then the number at 4 is going to be the next number in the data set. But we had it as 5, but it's 8. Why is that? Well, it basically added, if we compare these two together, it adds this, because this is at the 4th slot, with the 5 that was here before. See here, that's why it became 8. So all we have to do is basically add this, but we have to subtract the previous number. And then we're good. So, and this is the easy way to remember it. At slot 2 is 3, correct? Slot 2 is 3. And then here, at slot 4 is 5, the number that is in front of the minus sign. So that's how it goes. So if we wanted to add another one, we wanted to add the next, we would do this. We would have this, and then we want to add, let's say, I have to add. Let's say the next number, we have to subtract the previous. So this is the previous, so we have to subtract 5. And let's say it's, I don't know, let's make it a decimal now, 13.3. So we press enter, it's going to put 13.3 at 4, but we want to keep the 5 at 4. We have to multiply, we can't forget. So 2, 4, this is powers of 2. So the next is 8. At slot 2 is 3, right? At slot 4 is 5, right? Then at slot 8 is 13.3. So 1, 2, 3, 4, 5, 6, 7. So that's the idea behind it. It's really easy, right? You're just adding zeros to numbers. There's really nothing to it. So this is just showing 8 that we just used. So this is 1 starting at 8 and every multiple of 8 from that point. And the same will hold true for 16 as well, and so forth. That's how it goes. But you have to do it in powers of 2. That's the only way this works. Let's go to the original list of numbers that we saw matched in the beginning. So at slot 2 is 7. At slot 4 is 5.33. Then we have to go here. So at slot 8 is 3.6. Just look for the plus sign. At slot 16 is 2, and so forth. It goes all the way down until we get to here's the last plus sign. So at slot 128 is huge numbers, right? Is 0. And this is that you could sit here and count them to see that that's true, that what I just read to you matches this list, but we don't have to worry about that. Right from this point on, regarding this, you don't have to look at this list anymore. It should be apparent that is true. So I bet y'all are crying for me to do this, so I did it. I just wrote the denominators as powers of 2 to make it more uniform. That's all I did here. If we want to, instead of just saying at slot 2 for, let's say, like x equals 1, and then slot 4 for x equals 2, and slot 8 for x equals 3, right? That just doesn't really, it's not necessary to do that. We can make a small transformation to make it happen, that we can say, well, in this case it's n instead of x for the letter that I used, but you just say 2, and then this is going to be x equals, or say n equals 1. At n equals 1, the value is the bottom left corner here, it's 7. At n equals 2, the value is 5.33, and so forth. So all I did was I substituted in this for n instead of 1, 2, and 3, and so forth. So naturally, why would I want to say n equals 2 to the 2? I want to say n equals 2. So all you have to do that is just put it in. Put in 2 to the n instead of n inside of these expressions. We can combine the exponents to make it easier, but I don't do that later on, but I do that now just because. And I leave 1 in the denominator so that these expressions are still readable, because when it's all in one line, it becomes almost unreadable. So now what we're tempted to do is to factor out these cosine expressions from the whole function. So this is factoring out. I'm just going to talk in terms of this. This is n minus 1. I factored it out of all of this. So this is the previous. And this is now that I factored out the n minus 1 factor. Then I factored out n minus 2. It's getting smaller now. Then I factored out the n minus 3, n minus 4, n minus 5. I can factor out the n minus 6 as well. So that's all of them factored out. It looks much more like what we saw at the very beginning, and so we're getting there. To further write this more compactly, let's just create a custom defined function to abbreviate this cosine. So this is that expression, and so this is what we saw at the beginning. So that we're already there. Now this is only for the case when the values of x are 1, 2, all the way to n. So this is almost like a sequence, so to speak. It's not actually interpolation where x's can be negative values, they can be decimals and all that. We're going to cover that in a little bit. But for right now, that's where we're at. But just please go ahead and review what was talked about so far. Make sure you understand everything, and then we'll move on. So just looking at the top here, if we just define this as my function, this whole thing as my function, and then we evaluate it from 1 to 7, it spits out the list that we had originally, so therefore it's correct. We can graph this. When we graph it, it's clearly a trigonometric function. And the graph here is just basically color coded so that the same color is the same y value. So you can see that the y values repeat, and we could probably see that earlier from the list because we had like 5 starting at 2 and going every multiple of 2 from that point. There has to be something. There has to be a 0 or a 1 for the next one that you subtract to get the next value, something in order to stop that value from appearing, but otherwise it's going to appear. So from this and from this graph, maybe we look at the value at 0. It's a peak. It's a relative maxima. Then here too, relative maxima. 3 and 4. I don't know about 5. I have to scroll to the right to see it. It's a relative maxima. So you might be thinking that this method at the integer values creates the relative. It's at a relative maxima always. It's not true though. It's not true. We didn't see, I had values 6 through 7 as well. We didn't see that, but here they are. So value 6 is clearly a relative minima, and 7 is also. So it's just at the extrema. Not that it really means anything, but that's just what's going on. So I was thinking that maybe the applications of this would be some type of, I don't know, echo type interpolation instead of something like this where this is trigonometric interpolation I saw from the web, and it's kind of small to see. I guess I'll zoom in so you can see the URL so I'm not plagiarizing anybody. That's where I got this from, but this was just on the page 5 of 52 of that. So it fits this discrete graph very well, especially I guess this is for more iterations or something, so it fits it extremely well. And it's not like mine. This is the same type of discrete graph that you would have, like step functions, and it does whatever it wants to do. That's why I mentioned at the beginning of the video that this may not be actually practical to use to actually interpolate anything. This is just literally to be able to have a function that matches the values for whatever reason that would be. But it's just a method that I wanted to show because it's extremely easy, especially for the multivariate case. This is very easy also, but just that's just even easier when compared to other methods. So if I were to make a Mclaren series out of this, it really doesn't work out that well. This is the function in Mathematica to create a Mclaren series. Well, Taylor series actually, but this here is where it's centered at. So that's A in the Taylor series expansion, so it's 0 for Mclaren. So this is the polynomial I get, and if we were to graph this, it looks like this. It doesn't look anything like the data that we fitted. So I don't know how to graph too well in Mathematica. I think GeoGebra is much more user-friendly when you get to know it. But Mathematica has some very nice graphs regardless. But yeah, I can't zoom in or anything to see, but I doubt this would fit the data very well, but it might. But this is the polynomial. Just I made I don't know how many terms I said, 17 terms. The first 17 terms of the Taylor series for this function that we graphed here. That I graphed that Taylor series here. Okay. So, and just for those who are unsure, yeah, this is the Taylor series for cosine of x. I used the same thing, the Mclaren series. So there you go. We already know that's for cosine if you know calculus at all. If not, it's not a big deal. It's just for those who are curious to try to make this into a polynomial, that's all. And this is the graph. If we were to graph the polynomial for cosine of x from 0 to 2 pi, it fits it very well, right? It looks just like cosine. You can't really tell any difference. This is like cumulative pattern interpolation, echo interpolation, or just simple curve fitting. I don't know how you want to describe it. But yeah, this is for univariate interpolation. So this is to expand it to become more generalized. It's really not that hard. All we have to do is start from scratch. Well, not entirely from scratch. Basically, it's going to look a little bit different than this, but almost the same, but a little bit different. But how it looks, we have to derive it from the beginning to kind of make it into what it needs to be. We can't do any guessing. So let's say we have 3 data points and we have increasing values of x. We're going to see soon that it doesn't have to be increasing values of x, but this is just a simple case. At the value at x equals 3, the y value 7. That's how to read that. And this is the plus sign, so we start again. So now this is the highest power cosine. So the value at x equals 6 is 13. Then we go to the next plus sign. The value at x equals 8 is negative 16. Right? Because we subtract 13, which is the previous one, and we subtract 7, which was the previous one. So this is the exact same thing we did earlier, and I just left it like this, where I didn't say 2 to the n minus 3. I just said 2 to the n divided by 2 to the third power. That's how I kept it. But this will fit the curve exactly the way it's intended. So like this is x equals 3 and it's 7. This is x equals 6 and it's 13. And then this is x equals 8 and it's negative 16. So it works. We don't have to see all of these. We just can see that it works. What we want to do is factor out the cosines like we did before. So this is how it's going to end up when we factor out the cosine. These are the ones we factored out, that we could factor out at least. And this is what remains. So if we were to write this compactly by defining CS again to be this, it would be this. But this is not as easy to understand as if we were to write it vertically like we did before. I just rewrote this so that it's similar to what we've seen previously. So there's really no difference between now and the kind of form we saw previously, except that we have a product of these special cosine functions. And notice about them that we start with the first x value for the first instance, but then we just say that x value plus 1 multiplied by all consecutive ones increasing until we get to the next x value, and then we times that by the resulting needed y value for this x value. And we do the same here. So to test it real quick, evaluating it at 3 gives us 7. Evaluating at 5 gives us 7. Well, 5 doesn't matter, right? No. Evaluating at 6 gives us 13. And evaluating at 8 gives us negative 16. So that's all there is to it. To have not be restricted to x equals 1 through n for the x values to have a corresponding f of x value for each one. But we can write this more compactly like so. This is a product of factors. So we can have a lower bound and an upper bound. So here the lower bound is equal to the upper bound because there's only one term. So the product is going to execute just once. So we have that times 7. And then we have 4 to 6 times 13 minus 7, and then 7 to 8 times negative 16 minus 13. That's all there is to it. So it might be good if we abbreviate this. This was just another example I did. But we can abbreviate this product here by assigning another function, let's call it p, and it takes two arguments, the lower bound and the upper bound. The upper bound is going to be the actual x value, the lower bound is going to be the previous x value plus 1. That's how it works. Remember from before, we had like if we come here, this lower bound is equal to this plus 1. This lower bound is equal to this plus 1. So this is it abbreviated even more, and that's all we can really do from this point. Now this kind of resembles the multivariate case that we saw at the very beginning. So let's go to the multivariate case, where we're going to define a function for every single independent variable. In this case, these are ordered triples in the example that we showed at the beginning. I think it was I square root of -1, which was I instead of square root of 2. But it's the same otherwise, the data set here. So an expression for x, an identical expression for y, except I just changed the variable from x to y. And then I have to define a px and py for each of the cx and cy. So this is the idea behind the multivariate, is that what we saw before in the derivation for the univariate case. So if we want to input an x and a y and have still the same value, we can just simply put in x and y, have the same expression, and just divide this by 2. So x will contribute half of this number, y will contribute the other half. That's the main idea. So if we had x, y, z, t, where t is the dependent variable and x, y, z are independent variables, we would say 7 divided by 3 instead of 7 divided by 2. So that's the main idea behind it. So in this data set, instead of 17, we're going to have 17 divided by 2, because we have another 17 divided by 2 that the y part contributes. And we add these two functions together to get one multivariate function. One term is completely x dependent. One term is completely y dependent. Both terms are independent from each other. There's no mixture of x's and y's together. They're just added together, but it still works out, right? Why wouldn't it work out? We're basically doing the univariate twice. That's what we're doing. But we're using two different variables to determine that. But basically, the thing to notice now is, well, we're limited to something here? We have increasing values of x, and we have increasing values of y. Do they have to be increasing values of y in our data set for this to work? Are we limited to that? No, we're not. Take a look at this example. We have x is at 0, but then it decreases, then it increases. We have y starting at 230, then it decreases, and then it decreases again. So this is just a counterexample if this wasn't true. So the key thing is that for the x, negative 272 is first, but for y, negative 272 is second, because we still have to put the x values in increasing order and the y values in increasing order. But that doesn't mean that the values in the order pairs have to be in increasing order. Let me go back to the previous example. So this right here is less than this, which is less than this. This right here is less than this, which is less than this. But here it's not that way. This is greater than this, and this is less than this, and so forth. So that pattern is broken up, but all we have to do is just do it in order this way when we construct the function. Just trying to see what this multivariate function looks like that we constructed just to fit those three ordered triples. It's quite large, but it works and it's easy, right? Now if we were to graph this thing and take a look, we can notice here that this is the z-axis. It's supposed to be at negative 272 at its largest negative depth, but it doesn't really go there. I don't know what I did wrong with Mathematica. It just seemed not to graph it. Maybe it's too difficult. I don't know. I don't think anything's too difficult from Mathematica, but there's just something not right with it. But I did each separately. So this was the second order triple here. So when I graph this, it is supposed to be approaching the z value of negative 272, and that's down here, and it looks like it is, right? So it has to be correct. And this was another order triple of it. It's supposed to be approaching 17, and come here, and it looks like 17 is going to be a little bit greater than 0, so it looks like it's, instead of going from, let's see, it was bottom to top. No, it was the top to bottom. This is bottom to top. The direction in which it's going for some reason. I don't know, there's really no point to graphing these, but this is just for those who are curious and didn't want to have to do it themselves. And this is supposed to go to square root of 2, which is a little bit greater than 0, but it doesn't seem to make it. I don't know. Maybe it does. It can barely see it. Yeah, it might be at 0, but it's so close to 0, and these are increments of 20 that, yeah. Anyway. Alright, so far we have independent variables where they're all integers. But what if they are not integers? What if they're any real number? I don't know about imaginary numbers, but for real numbers, so that could be decimal, of course, right? Irrational numbers that you rounded at least. What about those? Can those be used for the independent variables for input? So right here, this was one of the previous examples. I changed it from 5 to 5.1. If we evaluate this at negative 5.1, then it doesn't give us the correct value. We're supposed to be getting 7, and then the next value, which should be at 4, that might give us the right value, but it probably won't. Well, it does. Okay, just magically it does. And then the other value would be at 8, at x equals 8, and it gives us negative 16. So it works somewhat, but at negative 5.1 it doesn't work. I mean, why would it? At this point, we really didn't do anything. We didn't do a transformation that's needed to take care of a decimal x value, for example, because we have cosine of integers, of multiples of pi over 2. That's going to be either negative 1, 0, or positive 1. So, of course, it's not going to work. It doesn't make sense. But if we do this, if we have 5.1, we just take the independent variable with the most number of decimal places, and we just multiply every single independent variable and the expected output number values by that power of 10 to make that biggest decimal a whole number, or I should say an integer. I shouldn't say whole number, because technically a negative integer is not a whole number. So that's what I did here. And so once you do that, you just divide the whole quantity by that power of 10 to compensate. So this is a way to do it generally. So we just have the power of 10, which we have to determine when we construct the function for interpolation or curve fitting. And so when we type in enter, indeed at x equals negative, or in this case it's n, but that's the same as x as it has been throughout this video, at negative 5.1, it's supposed to be 7, and it is. And so at 4, it's 13, and then at 8, it should be negative 16. So at 8, negative 16. So this works out for the multivariate case as well. But that's all there is to it. I mean, I don't think it can get any easier than that. Now, is it practical to use? I don't know. And it's definitely not practical to use for everything, because even the existing interpolation methods are not good for everything. But this may be good for something, but I just wanted to get this video out there. And again, the multivariate case is very easy. It's really nothing complicated in comparison to the univariate. It's just the same thing done twice in this example. Or if you have 3 independent variables, you're going to do it 3 times. Just add 3 different terms instead of 2 in this case, or instead of 1 for the univariate, you have 2 for the smallest multivariate case. And I didn't really mention this, but obviously we don't need to have 2 different specially defined functions for each independent variable. We can just have 1 for each independent variable. So we can just take this here and just substitute it for itself in here. This was just for the derivation of this method. That's all we have, just these 2. And another thing to also mention, which is probably obvious to anyone who knows cosine really well, if you have 2 to the k, some power k times pi, and then you square the quantity, you're going to get certain types of results, and that's it. You're going to either get 0, 1/2, or 1, or some other value that really cannot be simplified. And with this method, the values that cannot be simplified, those are going to be canceled out by the zeros that we multiply this expression by. So keeping that in mind, speaking in terms of evaluation, like in comparison with polynomial interpolation, I'm sure polynomial interpolation, and I know it is, I know of it, is that it's very good for fitting certain curves that this probably won't be able to. But like for the polynomials, you have to take a number and raise it to the 7th power for a polynomial of order 7, for example. So multiplying a number times itself 7 times, and that can be like a decimal or whatever, it's going to be very difficult computationally to do by hand. But this is rather trivial to do. That if it's a number like this where it doesn't really simplify down at all, it's not either 0 or 1 or 1/2 even, then you can automatically just discard it when you're evaluating this by hand if you wanted to evaluate it by hand. So it's very doable to do by hand compared to the actual type of functions that you get from Lagrange interpolation or something like that. Just to mention that. Yeah, but that's pretty much it.